I try mute my.
Tension is building.
Hello, everybody, and welcome to this week's Future in Space Hangout. My name is Tony Darnell from Astronomy.space, and today we are going to dive into the subject of landing humans on Mars. Our guests today are working on this problem, and I don't think it will surprise anyone watching here today that landing anything on the red planet, whether it's rovers or humans, is a very hard thing to do. So today we're going to discuss the problems of landing humans on Mars. What type of vehicle should we use, and where should we land once we get there, once we get humans actually in orbit around the planet? Now, I want to welcome everybody watching these Hangouts live, as we do these every Thursday at 3 o'clock Eastern Time. And if you missed the live broadcast, then I want to welcome all of you who are watching this on demand. That actually happens to be the bigger audience. But the big reason that we do this live is because we want to give you guys a chance to directly interact with our expert guests. So please leave your questions and comments in the YouTube live chat or on our Deep Astronomy Discord server, and I will read them out as we go along. And if you've missed the live stream, don't let that stop you. Go ahead and leave comments in the video below, and I will check them periodically and try to get an answer back to you. If I don't know it, I'll try to ask our guests via email. So before we start, one quick announcement before we get going here, and that is that if you want to be notified directly about when a new video is added or a new live stream has started on either deepastronomy.space or here on the YouTube channel, then head over to our webpage, deepastronomy.space, and register. All you have to do is leave your email, and if you opt into our notifications, you'll get an email every time something is added to our webpage or the YouTube channel. Now, we're doing this because the notification systems on YouTube are very strange and don't always work the way they should, and I have more control over it. And I promise you, if you give us your email address, that I will not use it for anything else but deep astronomy related stuff, and we don't sell it. Your privacy is guarded. We have a privacy policy on the website, so please check it out if you're concerned about that. So that would be the best way to learn about new content. So I just wanted to do a quick announcement there. Okay, so let me bring up my co-host and guests here. Joining me is, as he does every Future in Space Hangout, is Dr. Harley Thronson. He's down in the lower right corner. Hi, Harley.
Hi, good afternoon or good morning, or whenever you're watching.
Good evening if you're
evening,
yeah.
midnight.
Yeah. You want to give a little intro into our Hangout series and sponsor and all that kind of stuff?
Yeah, this is sponsored. And just as Tony said, we're doing this every Thursday. We're co-sponsored by the two AASs, the American Astronomical Society and the American Astronautical Society, as part of their initiatives in public engagement, public information, and we are very grateful for their support.
Yes, and I'm reading on the live chat that there apparently at 9 p.m. in the UK is a new show on BBC called Missions, which you guys need to check out because apparently it is about things like this. So we're going to set the stage for you on getting humans to Mars. Okay, my guests today. Let's start with introducing my guests. In the upper left panel there is Michelle Munk. She is the Entry, Descent, and Landing Systems Capability Lead at Langley NASA HQ, and she is going to talk to us about some of the thinking they've done with getting humans to Mars. In the panel right next to her is Dr. Marcus Landgraf. He works at the European Space Agency in the STEC division, the Technology Center. STEC stands for the European Space Technology Center, and he's currently working on landing on the moon, which I don't think it takes a big stretch to realize that we need to be able to do that as well, and what we learn by doing lunar landings will also attribute or go well towards helping us land on Mars. And then next to Harley down in the lower corner is Tara Polsgrove. She is the lander lead for the Mars Study Capability Team at Marshall Space Flight Center. So thank you guys for joining us. Welcome, everybody. I guess, Michelle, let's start with you. We've got your PowerPoint. I'm going to pull it up here in just a minute, but I thought maybe you could give us a little introduction into landing on Mars. What's the big deal? Why is it so hard?
It is hard. We've been, Tara and I have been cohorts in various studies for longer than I'd like to admit. And, we've sent 7 landers to Mars thus far successfully in the United States. And, we've had wonderful science returns from those missions. We've got Curiosity driving around the surface right now, and we're getting ready to send Mars 2020 in a couple years. And so everything's been going very well. But when we talk about sending humans to Mars, we'll tell you about why this is challenging. It's such a big difference in scale. Humans need a lot of stuff, so they need a lot of volume, and those are things that we don't have to worry about so much if we're sending science instruments. So we've been looking at this for quite a while. Our thinking has evolved, and I'm really excited that our analysis is getting to a level that it's never been at before. So I feel like we're really closer than ever to achieving the goal of landing humans on Mars.
Okay, so yeah, and Tara, we've talked a bit about before in the past about the steps of getting humans to Mars, getting equipment there first, using these space trucks, they're calling them, these electrically propelled engines to get us to Mars and get the stuff there that we need. But you guys are picking up the problem, and I guess this is how NASA does things, and maybe ESA does it too, I don't know. But you break the problem up into chunks, and you guys are focusing on the landing part, getting us from Mars orbit onto the surface, correct? And you, in particular, are looking at the lander part of it, right?
That's correct. So we've figured out kind of what kind of equipment a crew would need while they're on the surface. And, one unique thing about human missions is that our people want to come back home again. So our robotic missions, they don't have an ascent vehicle so far that they've had to land. And so that's
point.
Really,
they don't worry about that, do they?
That's really kind of the driving case that's sizing our human landers, is that ascent vehicle to get back off the surface again. And takes about twice as much energy to lift off the surface of Mars than it did the moon, because we've got more gravity there. It's a different scenario. So we've got a significant scale ascent vehicle that we have to deliver. And so that's leading us to the challenge that Michelle talked about, just a complete difference in scale between our experience base with the robotic landers and what we'll have to do for the moon, for human landers to Mars. Yeah,
and so I'm going to go ahead and bring this in. Buzzbox the Third on YouTube is commenting, and maybe Marcus, I can get your comment on this. Is like he's commenting, we should just land on Mars like NASA did on the moon, because that worked perfectly. Is that the kind of thing you're working on at ESA and landing us on the moon? Are you just going to redo what Apollo did, or are you looking at other issues?
That's a brilliant question, Tony. Really, what we're doing is we work with international partners, because we're, compared to NASA, we're pretty small space agency as everybody else is, I guess. And so we're really looking into roles we could play in the frame of the bigger picture. Now, the interesting bit for tonight is that the landing part is quite different between Mars and Moon, simply because there is no atmosphere on the Moon. We're 100% propulsive, so we're going down on riding a big rocket, backwards basically, and landing like Apollo did. The big difference between Apollo and the modern moon missions that we're considering together with international partners is the surface bit. So in the modern scenarios, we're not, working around the lander. We're actually exiting the lander and then leave for a month or so in a mobile vehicle. So we'll drive around a lot on the moon. There's a lot of driving going on. And that is going to be that part is going to be...
That's actually very American of you. Americans love their cars, you know.
Yeah. Germans do too. So.
That's true. Good point. That's true. Probably the only ones who like them as much as Americans. Yeah.
Might be a Beamer that we're driving around there. So, so that part of that mobility and surface operations, that is actually we think quite comparable and similar, and we can do a lot of risk reduction on the moon for preparation to going to Mars.
Right. So
it's my interest also to watch and listen tonight.
Yes, and you bring up a good point, of course, that there is no atmosphere on the moon, and so it sounds like the approach that ESA and you guys are taking is you're looking at maybe not doing something too dissimilar to what Apollo did. You're going to ride a rocket backwards, regardless of the shape, and what actually ends up happening. It's basically that that component. So I want to bring up this slide that Michelle gave me that I love it. So let me just hang on, give me a second to bring this up. And then I will do this. Let me get rid of that. Okay, so this is a slide of all of the human landers that we've sent so far to scale versus what we're going to be needing for a human-sized lander. Michelle, you want to comment on this slide a little bit?
Sure. Yeah. Dating way back to Viking, all of our robotic Mars landers or entry vehicles, the capsules that you see, enclosed in those aeroshell shapes, have looked pretty much the same. We call it the Viking architecture because it was invented then and it served us very well. So we have the 70-degree sphere cone in front of the payload that we're sending, the lander or the rover. And that's because that really shallow angle is to maximize the drag area. Since we have so little atmosphere at Mars, about 1/100th the density we have here on Earth, you really need to kind of flatten out your aeroshell and fly behind a dish. So, but you need a little angle for stability. So that's kind of the reasoning behind that four-body shape that's pointing to the left on the chart. And then the aft body is kind of designed to enclose whatever payload we have, but also it plays a role in aerodynamics, particularly at the low speeds. So, and all of these that you see here, Viking 1 and 2, Pathfinder, Spirit and Opportunity, Phoenix, MSL, and even Mars 2020, which is pretty much a carbon copy of MSL, they all used parachutes to slow down. And in the supersonic regime, low supersonic, and for people, for the human scale type of lander that you see depicted, artist depiction on the right there, parachutes really aren't effective. We would need a cluster of parachutes probably about as big as a football stadium to slow this vehicle down, and that's, that seems like it's too risky and very difficult to develop and flight qualify. So it's interesting what Marcus said is very appropriate, because in this case, for the human scale Mars landers, we're looking at propulsive approaches rather than, parachute approaches. So it starts to look a lot more like an Apollo style or a lunar landing as you get closer to the surface.
So that would mean then at some point that big disk at the bottom is going to have to be jettisoned if you're going to have room for a rocket to fire, correct?
Tara, you want to talk about that?
Well, that's one of the challenges that we're working through now. So we'd rather not jettison any components, because to build up our Mars equipment and infrastructure, we'll have several landers. And so we don't want the potential to impact any of our existing surface assets. It's also maybe a little bit difficult to separate that big aerodynamic force when the air is pushing it against the vehicle. So we've actually got in our current designs, we've got holes through that heat shield that would open up and expose the engine bells, and then we'd be firing through it. And then once we land on the surface, we'd have to retract or some way dispose of that heat shield so that we can have access to our payloads, which would be sitting on top.
Am I reading this right? It says the entry mass is 47 to 62 tons. What's that T?
That's right. That's metric tons. So a ton is 1,000 kilograms. Yep.
Wow.
Yeah. So, that's the mass at the top of the atmosphere. In order to get what we're planning on a 20-ton payload. And as Tara recognized earlier, the ascent vehicle to get the humans back off the surface is the kind of the driver for that mass. It's the largest indivisible piece that we need to put down. We can't really break it into smaller parts. And so in order to get 20 tons of payload, that ascent vehicle to the surface, we need about 50-ish tons at the top of the atmosphere. And that means we're landing, with our aeroshell mass and everything, around 40 tons on the surface to get that 20 tons of useful payload.
Yeah, that getting back off again part, that seems to be a real pain in the. Of
course, one day the plan is, maybe decades from now, is that you won't return. You won't need to return. Folks will be there permanently. I was noting one thing. I think I know the answer, but that the elevation at which it would land was what was it, +2 kilometers, whereas the robotic missions were below the mean surface elevation of Mars.
Right, kind of like yeah. Yeah, so there have been some landing site workshops, and at this point we'd like not to have to restrict the surface where we can take the humans on the surface. And so you also notice that Mars Science Laboratory landed in Gale Crater at a negative 4.5 kilometers altitude. And what that does is, since Mars Science Laboratory is about 1 metric ton, it's the biggest thing, heaviest thing we've ever put on the Mars surface, that gives you that extra distance to bleed off more energy from the thin Martian atmosphere. So every kilometer of altitude is precious to you when you're trying to slow down. So for the humans, though, to keep all of our landing site options open, we'd like to have the capability to land them at +2 kilometers, so above the kind of sea level. So we're even taking, it's even a more challenging problem to land that big mass at that higher altitude.
So Michelle, can I chime in here?
Yeah, by all means.
That sounds very interesting. That seems to be driving your whole design towards a more propulsive solution compared to the robotic missions. Is that a fair statement?
I wouldn't say it's just really the altitude that's driving us. Even if we said we were landing at -4 or 0, I think parachutes are still not a viable option. Okay. It's really the mass as the driver.
Okay, mass to area ratio, I suppose. That's kind of the driving parameter.
Absolutely. Okay. So, to talk about that area ratio a little bit, again, the challenge at Mars is that thin atmosphere, and we only have so big launch vehicles, right? Our launch vehicles are only a few meters in diameter. So the Mars Science Laboratory heat shield was 4.57 meters in diameter to fit inside a 6-meter launch vehicle shroud. And so we're assuming that we have a 10-meter shroud on NASA's Space Launch System. But we need a lot more drag area than that to slow us down. So we're really looking, that's driven us into the area of deployable decelerators. And we have a couple concepts that we're looking at. One is a rigid deployable, kind of like an umbrella. And then the other is an inflatable technology. So in both cases, you stay kind of folded up so that you can fit inside the launch vehicle. And then before entry, you deploy your large area aeroshell to slow you down.
Okay, Rami Emad is asking, and I guess I need a little clarification on this too. He's asking, I didn't understand why humans need to land at +2 kilometers. I understood the other one where you land in a crater, you get all the space you need for braking, but why the +2? Tara?
Well, Harley or Tara might want to chime in here. I haven't been at the landing site workshops, but I think at this point we're trying not to restrict ourselves. But again, even if we tried to land 20 tons at -2 or -4, I don't think it would make that much of a difference in our system.
I get it. By setting that as the level at which you can operate, you're basically saying we can land most places on Mars.
Yeah, it may be helpful to jump to that slide deck. I think the very next slide shows you a map, and you can see the surface area that you could gain access to if you could land at a little bit higher altitudes.
Let me pull that up. Is it this one here?
That's the one.
Okay, so well, go ahead, Tara. Explain.
Well, I think this is Michelle's charts. You can jump in and correct me if I'm wrong, but the 0 MOLA there is kind of the yellowish color. So your blues and greens are negative altitude there, and that's where we.
What's MOLA stand for?
Mean orbital. Go ahead, Michelle.
It's a bad acronym, and we use it incorrectly. MOLA is actually the Mars Orbiter Laser Altimeter, which is the instrument that was used to gather the data to kind of tell us where sea level is. So we're kind of just talking about Mars sea level or 0 elevation when we say MOLA.
Got it. And so the yellow is that pretty much 0 level then.
Right. So if we can design our landers to give us access to sites that are 2 kilometers above that, then you get access to all those orange areas as well. So it opens up your opportunities for landing sites.
And these areas up here, these grayed out areas, these are sort of not considered. So with this +2 elevation, you can basically land anywhere in here.
Anywhere that's not grayed out. Yep.
Except for this right here, which looks like Olympus Mons. So
yeah, and the grayed out areas are more for, I believe, it says at the top there, they put a latitude limit on it, which is independent of the elevation, but it increases your ability to utilize solar power on the surface if you're at a lower latitude. So, that's one of the possible ground rules that we are trading currently. What is our surface power source, nuclear or solar, and is solar feasible?
Are you guys working on that question at all, or are you just focused on the getting of the landing done? Because I'm curious about that too, whether it's solar or nuclear that's winning out. But that may be a little outside the realm of this hangout. So the okay, so that was a good question. So that's why the +2, so let's talk a little bit about what we need to get the landing done. And you guys have a little slide here that let me pull this back up. Here we are, and it says that. Well, Michelle, can you guide us through this one?
Sure. I'm going to introduce it, and I'll turn it over to Tara because this is her baby. Okay. This kind of defines what we need to land. So even prior to there being an entry, descent, and landing team, the Mars architecture team at NASA was defining the mission. So, how many people do we want to send? How long do we want them to stay there? And so those decisions drive the amount of stuff you need to take. So you'll see here that, they assumed a 10-meter diameter space launch system fairing. They wanted to send a crew of 4, and it was a 300-day stay, or for, orbital mechanics geeks, a conjunction class mission as opposed to a 1-month stay. And so that drove us to this kind of manifest of 4 20-ton payloads that Tara can tell you more about.
Okay.
Right. So this is one example. Obviously we still have a lot of trades on the table. This is an example manifest that we use, and it's really important for the lander design to get a look at the payloads that we have to package just volumetrically, and just seeing the different shapes and ways that they are grouped together kind of tells us things about how we need to design the lander. So we need to be flexible to different types of payload layouts. We need to be able to enable payload offloading. So those kind of things factor into how we need to do the lander design. And you'll see on here, Lander 3 has a rover on it. So like Mark was talking about, if we get experience on the lunar surface with rovers interacting with habitats and other elements on the surface, that's going to directly relate to kind of how we execute surface ops on the Martian surface as well.
Marcus, are your rovers they're going to be driving around your beamers, the lunar beamers, are they pressurized or not?
Yes, they are. So they're the main habitation for the current lunar scenario. So you're talking about taking 4 guys and gals on the surface, and each pair has a rover. So there's 2 each in a rover. That's the current scenario, and it's probably, we believe it's very Mars-like. So they spend all the days and nights, and on the moon the day is 14 days, Earth days, and the night is 14 Earth days. So that's going to be a very interesting scenario, also power-wise. And our current solution to that is a hybrid, nuclear solar hybrid, and that makes it very interesting to also look at that if you talk about Mars, and then how that changes the solution space.
Where Marcus, you're looking at solar during lunar day and nuclear solar night.
Basically, yes, correct. So the night there's not different kind of operations, and the challenge on the moon is to stay warm during that night. And then the nuclear power sources are good at being a very reliable source of heat. While during the day, particularly on the moon, we have the full sunlight with a full 1.3 kilowatts per square meter. So we'll use that solar power for sure to drive around on the lunar surface. And on Mars, that might be not too dissimilar, I believe.
One of the things I was going to ask, and I may have missed it for Michelle or Tara, the 4 landers that you had there in your current scenario, they would not all, of course, be landed simultaneously, but rather over a couple of Martian years, or over 1.5 Martian years, something. They will be emplaced and ascertain that they're working fine and everything landed fine and they're ready for the humans. And then number 4 will bring the humans down. Correct?
That's absolutely right. So one of the things this particular scenario relies on is propellant production while we're on the surface of Mars. So Lander 1 delivers our surface power units and some other cargo and logistics, and Lander 2 delivers our Mars ascent vehicle. And so the liftoff mass for the ascent vehicle is over 40 metric tons, but we're able to get that mass down to around 20 metric tons if we deliver the ascent vehicle without liquid oxygen propellant. And so it's fairly straightforward, we believe, to pull in the carbon dioxide atmosphere of Mars, and using our power systems and processes to convert that into oxygen, or strip that away and break it up into oxygen and liquefy that to fill up those Mars ascent vehicle tanks. And of course, we would confirm that all of that has completed and that the MAV tanks are full and ready to go before we ever commit to sending the crew to the surface. So that does take place a year or 2 before the crew arrive. And correct, the crew would come on that last lander in their habitat that they'll live in the surface.
So by assuming that you're creating the oxygen on the surface in situ, you can reduce the mass by half?
Right. So we've got, we're assuming a LOX methane propulsion system, which has a pretty high mixture ratio. And so the majority of that propellant is oxygen, liquid oxygen. So, right. So it's a great way. It's a huge benefit to take existing resources at Mars and use them to help us keep the landers small and have to bring less from Earth.
Okay, now from listening to you guys talk, one of the things that I'm struck by is that you're doing a great job thinking about the problem of getting humans down onto the surface. But are you given anything else to work with? I mean, it sounds like you have to solve this problem with an idea towards, well, we don't really know how we're going to what the context of the problem is. So you're setting up the solutions. Well, if we have this, then this is the lander we'll use. If we have these conditions, then if we use the SLS, then we'll use these conditions. Do you know what I mean? Are you sort of trying to keep your solutions as open as possible at this point, because you don't really have anything else to work with as far as a defined mission program?
Yeah, I can take that one. Absolutely. And I think, as we think through this, we've been looking at 4 candidate entry, descent, and landing, or EDL architectures over the past couple years. The ones that have kind of, some have been on our list historically for a long time. And so if you're familiar with the design reference architectures from NASA that have been published in the past, you'll see some commonality. But our thinking has also evolved over the past few years as new technologies have become available, like the high temperature soft goods that make up the inflatable decelerator. That wasn't possible 20 years ago when we published the very early design reference architectures. So you will see some heritage things and some more evolutionary things creeping in there.
Okay, I'm going to get a couple of questions before we get too far along, but let me remind everybody, you are watching the Deep Astronomy's Future in Space Hangout, where today we are talking about the problem of going to Mars and specifically landing human beings on the surface. And our guests today are from NASA HQ, Langley, and from the European Space Agency. We have Michelle Munk. She's the Entry, Descent, and Landing Systems Capability Lead. Tara Polsgrove is the Lander Lead for the Mars Study Capability Team. As well as Dr. Marcus Landgraf. He is from ESA, the European Space Technology Center, where he is working on landing on the moon. So that's our hangout. And I want to get to a question that, if I can pull it up, that Dark Time has asked on the Discord channel on Deep Astronomy. He's asking, why not go to the moons of Mars? No need for EDL or Mars ascent, just microgravity operations that we've well trained for. We're using the ISS. And my immediate comment is, well, that's a good way to land on the moon on Mars, but not Mars. But anyway, is there any thought to that? Maybe making it a 2-stage process where you start off being on the moons?
Yeah, that's something that's been studied over the last few years. We certainly could go to the moons of Mars. But I think the ultimate goal really is to land on the Mars surface itself. So the moons of Mars have some resources, but we don't think that's enough to sustain long duration presence. Whereas the surface of Mars, we know has abundant water now and other resources that we can use to sustain a longer term presence. Also, there's a lot of questions about Mars itself that we want to answer that'll be on the surface. But I do think going to the moons is an interesting option, an interesting thing we could do as we're preparing to go to the surface.
Okay, and Adam's asking, will human Mars missions need to loiter in orbit? I don't think loitering is the right term, in orbit before they actually go down. Will you need to be in orbit for a while to prepare to go down?
So I'll take a stab at that. So once we get into orbit, there'll be some sort of period of time to be determined really about lining up with the landing site, but also just a short period of time in orbit can help us really understand our position very well, which will enable us to have precision landing once we do begin the descent to the surface. So it makes sense to have some period of loitering or orbiting Mars before we go down.
I just have this image of these guys just sort of chilling, up in orbit. Somehow I don't think
that's actually a word that's used in operations.
Oh, it actually is a word.
Yeah, it's a word.
And you call it loiter. Okay.
Yeah.
Okay, so Adam's using it right. I'm the one that's like off on it. I just thought, I'm sorry, it just made different images pop into my head. So Upcycle Electronics is asking, what kind of redundancy is anticipated for the moon and Mars? If something goes wrong, would there be potential to leave early, or is there a plan to support the crew in case of emergency? And I'll leave that to you. And Marcus, you can comment on the moon part.
Right. if I may start on the moon, that's actually one of the reasons we're very interested in preparing some of the Mars operations on the moon, because the moon, first of all, is reachable every day of the year. So you can launch every day of the year to the moon, always. And the other reason is that you can, once you're on the moon, you can go home basically every day. And that's one function of the Deep Space Gateway, or now Lunar Orbit Platform Gateway, to enable this safe haven thing. So, but in the process of doing this, of preparing the operations, we'll become more and more independent from this option to go home, because we're not more confident every time we do the mission. And the idea is then to enable these mission scenarios that go to Mars and potentially have much more severe constraints on abort scenarios.
Okay. And what about, somebody want to comment on the Mars redundancies that you anticipate, the Mars landers? If something goes wrong, what's the plan?
Yeah, I think what Mark stated is exactly correct. As we get towards Mars missions, we have to be much more independent. We'll have infrastructure on the surface, and we'll have infrastructure waiting in orbit. So our Earth return vehicle will be waiting for the crew in orbit, but there isn't really an opportunity to come all the way back to Earth early. So you have to wait for those planetary alignments to get in the correct position before you can come home. So you can potentially leave the surface early and go back to your Earth return vehicle if that is a better scenario, depending on whatever the failure is. But we're going to have to learn to be more independent, have highly reliable systems, and have the astronauts able to make decisions in real time without real time support from Earth as well. So there's a comm delay too that they'll have to adjust to.
Okay, I just realized I had that lower third up for
actually, so I'd like to add a little bit. That's one of the real challenges of human missions to Mars. It is, you don't want to make it a one-way trip. Oh, you want to bring folks home, but it is difficult to bring them home once they are, first of all, underway toward Mars. I think there are a couple of your day or two out, or so I think there's some abort scenarios that can bring folks back home to Earth within a few weeks or something like that. But once you've been underway to Mars for the first, I'm doing this from memory, the first few weeks, you're going to Mars. Yeah. You're not going to come home easily. And then, of course, once you're at Mars or you're on the surface, and this was, I think, just the point that Tara made, that you're on the surface of Mars, you need to get home. You may be able to abort to your orbiting spacecraft. That might be just fine. But there are only a few times during the year, a few times when the Earth and Mars are suitably aligned, that you can get back from orbit to Earth. So it's something of a challenge. Here, and so maybe a little bit of trivia. And I guess this is something that Tara would know. There is in the current design for the landing system, there is an abort to orbit when you are on the way down. Yes, if something goes bad, you're landing. You can, and you don't want to land. Can you abort to orbit?
So right now we're focusing on just figuring out how to land. So there are some significant challenges on just getting a vehicle of this scale, lighting the engines supersonically, and the interaction of the engine plumes with the supersonic airflow around. And so we're diving into the feasibility of landing a vehicle of this scale. But the very next step is to go through and assess all the potential failure modes and all the possible abort scenarios. And so I think we've done just a little bit scratching the surface there of what might be possible, but I think it's too early to say really what will definitely be enabled and what won't.
Has that been tested yet, that idea of firing rockets at supersonic speeds? Have we tested that here on Earth at all, or is that a brand new thing?
You're asking my question. And in fact, actually, there's some great stories, which I think our guests will know better than I about, in fact, testing that capability high in the Earth's atmosphere.
Yeah, we've actually, that's something that SpaceX performs when they return their rocket stage to the barge. They actually light those engines at supersonic velocities and at a region in the Earth's atmosphere that's not too unlike the kind of density region that we'd see at Mars when we're trying to light our engines for landing. So in the past, we've had partnership with SpaceX to get some of their data and look at how well we can model what they measured on their flights. And so that was a very productive collaboration. And I think it gave everybody some confidence that lighting an engine, in that type of regime is not as big of a challenge as you might think. We still have quite a bit of work to do, as Tara alluded to, about understanding how that flow field comes back on a particular shape of vehicle. But I think we're pretty confident that we can start an engine with an oncoming supersonic flow that's of low density.
I guess you think about it, the engine bell is the exact wrong shape for for the direction you're going in to try and fire that rocket with catching all that atmosphere. Okay, good. So SpaceX has been working quite a bit on this problem, and are you confident then, Tara, that maybe these rockets can fire lower down, or do you even want? Well, let me rephrase that. At what altitude would be ideal for starting to fire these rockets on Mars?
Michelle may remember better than I, but I'm thinking we're at like 5 to 8 kilometers altitude, depending on what concept we're looking at, and in the around Mach 2 starting condition.
Right. We're looking at two very different classes of vehicles. One that's kind of like a plate coming in, a flat plate coming into the atmosphere, and then one that's more like a bullet or a brick coming into the atmosphere. So low ballistic coefficient in the first case, low mass to area ratio or lower. Versus higher. And so those two different kind of bounds to the problem kind of show you what our ranges are. So I see that you got the graphic up there. If you want to go to one of the next ones. Yes, this one. So we call this the mid L over D vehicle. It's got a kind of middle range, a lift to drag ratio. So it flies kind of like the space shuttle, kind of belly first to maximize the drag area and the deceleration. And then it comes in and you can see it lands horizontally. And the engines are kind of in the bottom on the sides. So this is one of our configurations that we're studying right now. And sorry, I can't see here we go. So this one you'll see the powered descent initiation kind of in the middle of the page is at about Mach 2 to 2 times the speed of sound at Mars at an altitude around 3 kilometers. But if you go to the next slide in the package, this is what we call low ballistic coefficient vehicle. This one's actually the mechanical deployable decelerator that kind of operates like an umbrella. And you can see that power descent initiation kind of in the middle right of the page is at 3 times the speed of sound. So not too much different, but at an altitude of 8 kilometers. So in this scenario, we're coming down a lot more vertically on top of our landing site. And that may enable our sensors to acquire the surface at a higher altitude and, kind of help us do a more precise landing. But that's some of the depth of analysis that we're just getting into with Tara's team now, so that we can kind of find the discriminators between, approaching with a high ballistic coefficient vehicle versus the low.
And this also shows what Tara was talking about earlier about the rockets going through the shield. Right? Down in this part here.
Right.
Yeah.
And if you look on the left, we've got kind of a bottom view of the vehicle. So you see some of the cutouts that we have to have for the landing gear and the nozzles. Okay. So it's going to be quite a challenge structurally to make all that work.
And the 4. I think it was where was that slide with the 4 different ones? Well, never mind. These were this one. I'm sorry, this one and the mid one. These were the 2 you're looking at as the most promising ones, correct?
We're actually looking at this mid L/D one, and then the last one, the inflatable, the hypersonic inflatable aerodynamic decelerator. There you go.
Okay.
And so the inflatable is a little bit lower mass for launch and entry, as you'll see. Just because of the structural mass of the aeroshell compared to the rigid. And so, but they fly about the same. So we're choosing the HIAD for now with kind of the same performance characteristics as the umbrella.
Hypersonic inflatable aerodynamic decelerator.
Yep.
And, okay, and that.
No, there.
So was that one back? Did we have one of those? Is that this one? No.
Yes, it's depicted there. It's depicted in several places because, it's one of our leading contenders for a few reasons. One is that, it has a ballistic coefficient and flight characteristics more in line with the robotic missions that we've sent to Mars in the past. It also, as you can see, the payload is not covered by a rigid shell in the back, and so it's very flexible to different payloads and packaging those. It may have some advantages for thermal control and communications as well. And of course, it's the lightest mass, so that's always a good feature to have.
Got it. Yeah. Okay. So there was a question I wanted to get to from Achilles. I've had this one queued up for a bit. Is there any payload advantage by landing higher on Mars? With the less atmosphere to launch through on return, do you get more payload? So is there any payload advantage to landing higher on Mars? Can you carry more stuff away?
I think Tara would love to launch from Olympus Mons, but I don't land there.
That's
right.
Right,
Because you need that atmosphere. Like you were saying, to get down safely, you want as much space as you could possibly get. That's why you're landing things in holes and craters and stuff. But getting off again, you kind of want the other thing, the exact opposite. You want to be as high as possible, right? Okay, good question, though. And Andrew Planet was asking, where's his question? Hi, Andrew, by the way. It's good to see you again. Could we send a small solar-powered bulldozer to Mars so that it could flatten a stretch of land so that we can later land missions on Mars like an airplane gliding down aided by rockets? Oh, that's not a bad idea. Could we send out bulldozers and then make a runway?
You could. I actually had a meeting this morning on the question of whether or not we need to prepare our landing site before we arrive. So with the potential for accessing water ice below the surface, it may be that you have excavation equipment there for other purposes. We haven't looked specifically at winged landers ever that I know of. We've looked at airplanes, but as science payloads rather than for an actual human landing vehicle. But, wings don't do you a whole lot of good at Mars because, again, you don't have a lot of density, so they have to be really big wings.
Okay, so yeah, and what are your consensus? And maybe Marcus, you can talk a little bit about the moon as well. Is there much talk about preparing, either robotically or otherwise, the surface before you land on either the moon or Mars?
Well, for the moon, certainly there's ideas to do so, but in general, the idea is, of course, that for the first missions, it's not efficient cost-wise to start preparing a lot of infrastructure before you land. So for the first missions, it's a little bit like the early discoverers, right? So you go and live off the land, whatever you find there. Once there's a system in place, and that's under discussion for the moon for sure, that if there's a regular traffic to the moon and more permanent habitation of the moon, then it might be possible or even be efficient to have more infrastructure like landing pads or caves or 3D printed habitats that then create a little bit of infrastructure locally, but certainly not for the first couple of missions. So that would be the situation on the moon. I think it's similar on Mars, isn't it?
Yeah. So one of the challenges of landing large things on the moon or Mars is that we've got a significant amount of thrust as we get close to the surface, and you may have some excavation or cratering of the regolith as you get close to it. So that's a challenge that we're actively trying to understand and model and do some testing so we can validate our models to predict what kind of site alteration we may see for landers of this scale. And so what we learn on the moon will certainly help us to better model and predict what kind of effect these engine plumes are going to have on the surface of Mars.
Well, while we're on this topic, let me ask Howard Kuhlman's question about how our plan. This is in reference to going to the moon, and I think NASA's effort. So, how are plans to go to Mars affected by James Bridenstine's unexpected cancellation of another moon landing, and what reason was given for the cancellation? Anybody want to comment on that?
Our new administrator briefed the employees just this morning for the first time, and he's been on the job for about 3.5 weeks. So there was actually a question asked about resource prospector, and I don't think it's being communicated exactly what all of the decision reasons are, but I think in the future. He did say that we will be resource prospecting on the moon. And so it may be that, we've been asked to work with commercial entities on small landers as kind of our first step on the moon. And maybe, there was a decision to get that going and see how that progresses before we, commit to a NASA-centric lander in the near term. So I think there's a lot of aspects of the NASA lunar initiative that are yet to be revealed. And so we're all waiting to see. But, one thing's for sure, as we were discussing earlier, there are lots of commonalities between the moon and Mars. And so Tara and I are working on things like, the common engines, precision landing technologies, and things that will really feed forward to the moon, surface power, and all those types of developments.
Yeah, I can see that there's a lot of overlap between the two efforts. And I guess going back to my initial question about the context of you guys solving these problems without any clear path getting us to Mars, are you finding, has your efforts changed at all what you're doing working on Mars landers and getting us down on the surface with the new emphasis on getting, NASA's supposedly new emphasis on getting to the moon versus its previous emphasis of getting us to Mars? Does that change you guys' focus very much, or are you pretty much still right where you always were, solving your problems?
We've been told that, we are still, Mars is still the ultimate destination, which is great to hear. And we're doing these two in parallel. I'm sorry, my light in my office has gone off because
you have to wave your arms. That's
wave my arm now.
Yes.
There we go.
There you go. Yes, I've been in many of those offices.
Yeah. But so we're supposed to be working both, which is great to hear. We're really, I think, getting to a great place on the Mars analysis. We're really starting to understand things and drive the technology investments. So, but putting the moon, in that path actually gives us an opportunity to pull some of the common technology maturation forward. So from my perspective at headquarters, we've put a greater emphasis on precision landing capability with the possibility of demonstrating that on lunar landers earlier than we might have sent a demonstration to Mars. So I think it's really exciting that we're accelerating some of these technology developments because of the lunar focus.
And
Tony, if I might chime in here.
You may.
if it's played right, I think there's a great opportunity to, by putting the moon there by NASA, to even accelerate the Mars effort if it's played right. So, give you an example. If for example, if we,
caveat.
ESA and JAXA, CSA would focus on the lander, while NASA puts more effort on the rover, which is 90% applicable to Mars, then both programs are affordable and they can actually de-risk each other. So that actually we could accelerate getting to Mars by using the moon in an international scenario.
Well, how much are your efforts at ESA depending on this? Let's say, NASA is currently emphasizing the moon, and you guys are going to the moon, right? I mean, you guys have already committed. You're going. You're working on landers. How dependent are you on NASA to do this? Or are you guys just doing your own thing?
We're 100% depending on NASA, to be honest. I mean, it's not like we're doing that in the vacuum out there.
Sure.
So NASA's going to lead the moon effort, and that's for sure. And if NASA would tomorrow say we're never ever go to the moon, then we would stop. It's very clear. However, by this little part, that's our niche in the ecosystem. The lander is the one that is a little bit more specific to the moon than the other parts of the infrastructure, and so NASA could focus on the SLS, on the Lunar Orbital Platform Gateway, and on the pressurized rover, which are all applicable and highly relevant for the Mars scenario. While if JAXA, NASA, JAXA, ESA, and CSA are looking at the components of the lander, and some robotics on the surface, then we would end up with a very harmonious pictures, which all gets us to where we want to go earlier. That's kind of the idea.
That would be awesome. And JAXA, for those of you who don't know, that's the Japanese aerospace agency. One plot is echoing what Dark Time. You guys don't want to go to Mars. You guys want to just hover around. One plot is going, why not build a manned Mars space station and have it orbiting Mars with drop-down missions? These guys are very tentative, okay? I can see that now. They want to go to the moons first, and then they want to go in orbit first. What do you guys think? Is any... why not build an orbiting space station around Mars first? Any talk of that? No?
Well, sure. There's been talk of what a crew could do in Mars orbit. So we could teleoperate rovers on Mars a lot faster than maybe we could do with the time lag going back to Earth and back out to Mars. So that's an option. Mars sample return. You could have robotic landers go down and samples come up and do some analysis in an orbiting station there. So who knows? That could be something that we do before we send landers down to the surface, human landers down to the surface.
Yeah. Andrew Planet, has the SpaceX landing boosters made other forms of landing on a planet obsolete? I'm not sure it would have made them obsolete, but it's certainly doing a lot of important testing, isn't it, for firing retro rockets to slow us down and land.
Yeah, I would agree that we definitely, as I explained earlier, have used some of their flights as, gotten the test data, and it's shown us some of the things that are possible that we had not embarked on yet. I guess one thing to remember is that, at Earth, we have a very nice global positioning system. We have very high fidelity maps of the surface. And so I definitely don't want to imply that it's easy to land on the Earth, because it's not. But there are some unique challenges with going to a far body where you don't have that infrastructure in place.
I tell you, another thing they've really got down is landing precisely. I mean, I remember when I first heard about they're going to land these boosters on what? A floating unmanned barge sitting out in the middle of the ocean, bobbing up and down. Are you kidding? I didn't think they were ever going to get that. But not only have they perfected it, they nail it every time. If you watch the booster landings, they're in the circle, folks. They're in the circle. It's amazing. So they've got pinpoint landings down as well. So SpaceX is gaining some really amazing expertise, and that I think could be used in getting us to Mars. What do you guys think?
Yeah, absolutely. We need to leverage everything we can, all the expertise that's out there around the world. So it's great to see them able to do that. I really enjoyed the two boosters coming down at the same time. I mean,
me too. I saw that live. I saw that on site. That was amazing. Yeah. Okay, so we're out of time, but I just want to get Achilles 308 comment. It'll be the last word on this. He says, if you guys are taking votes, I like the mid idea better personally. The forces on the umbrella heat shield will be very difficult to account for. And that was the option where that was that space shuttle body looking thing that went down horizontally and then the rockets fired. You have one vote for that, folks. I don't know if it matters, but he's a good space fan.
We'll add it to the tally.
That's right, and he knows his stuff, Achilles. I appreciate his comment. So thank you, Achilles 308. Okay. That is it, folks. We are done this week. We are out of time, but I want to thank all of my guests. Dr. Marcus Landgraf, he's from ESA, the European Space Technology Center, working on landing us on the moon. Thank you, Marcus, for joining us. Michelle Munk is the Entry, Descent, and Landing Systems Capability Lead at Langley, and Tara Polsgrove is the Lander Lead for the Mars Study Capability Team at Marshall Space Flight Center, and of course, Dr. Harley Thronson from Goddard Space Flight Center down below. On behalf of all of our guests and co-hosts, I want to thank you all for watching, and as always, keep looking up. Oh, I have a Royal Canadian Mounted Police one. Gravitational rubber duckies, folks. Help us come up with names. Yeah. Alrighty, folks. Thank you all for watching. We'll see you next week. Oh, next week will be the discussion of the discovery of using Galileo data of the plumes on Europa. We're going to be talking about that on the Astro Coffee Hangout next week with Dr. Carol Christian. Thank you all for watching. See you next time. And as always, keep looking up.